In example problem D2.2, we had a simply supported beam with a midspan load, and we were asked to find the maximum deflection for that particular loading scenario. And we've walked our way all the way through here of finding the reactions, finding the shear in the moment diagram in a conventional way, then observing what those equations would be for each segment. We did it that way because that was straightforward and easier to do than see through the formal differential equation approach. Then we have displacement, boundary, and continuity conditions that set up then displacements at two particular locations of continuity in the segment of the solutions there in the middle. And we got moment curvature. We've got these slopes that we find by integrating curvature. That's two different segments because functionally that's the way it worked out. And they're a pain, right? We get these, we can come up ultimately with a relationship between C1 and C2 that we find by using this continuity condition here, and it gets very lengthy all the way through, and all you can ultimately do is get this kind of an expression, but that's one of the equations that we're working with, right? So that's, say, equation 1 that will be useful. And then we come along and we have the slope equations, which we then integrate again, and we segment 1, segment 2 again. One of the boundary conditions is easy to work with, and we find out that one of these four constants is C3. So that's one of our, that is an equation, but it's an answer or result. We can let that go. But then we got to go deal with the other boundary condition, from which we only find out a relationship between C2 and C4. We haven't written it out here, but this is going to give us equation 2. And then we have the continuity condition that to the left and right of the midspan, these two displacement functions here have to be the same. That's our equation 3. So we end up with three equations in these three unknown constants, C1, C2, and C4. A lot of little tedious work to have to go back through and solve for those. But you do that, and then you go and you find out where the first derivative of all of that stuff is equal to 0. That will be at the midspan. And you'll find out when you plug back into your displacement equations that delta max equals PL cubed over 48 EI. Of course, that's happening at the midspan. That's what you've got to go and work on yourself to prove that that really is the case.